Hey guys, and welcome back. Today's video is specifically on chemical reactions, and that's what we're studying today. And I'll draw that line if you're trying to take notes off of this. But anyway, what we're really looking at is this concept of chemical equations. We're going to look at the four main types of reactions as well. So first, let's just look at a general chemical equation, what we see written out here. And so in this case, we see sodium hydroxide. You should be able to name this stuff now. HCl starts with an H. It's a binary acid, hydrochloric acid, reacts to create hydrogen hydroxide and sodium chloride. So you need to learn a couple of little vocabulary words right off the bat. You see anything on the left side, and when I say left side, you should be wondering, what does left side mean? Well, this little arrow means basically yields. So anything to the left side of the yield arrow, those are the reactants. That's what's going to react. Anything to the right side is what we call a product. That's something that you make in the reaction. So even in this simple little reaction, something should be obvious to you. All that happened is the hydroxide polyatomic and the chlorine traded places. So on the other side, the chlorine is now with the Na, and the hydroxide is now with the H. And one thing you should be asking, well, Mr. Cole, what if we wrote for an answer NaCl plus HOH? Would we still be right? Yeah, the order that we wrote those down in doesn't matter. It's irrelevant. What about this, Mr. Cole? H2HOH. Couldn't we write as H2O? Yeah, you're still right. That's certainly fine to write H2O on the other side. A lot of times it's just handy to write like the HOH down that way. So now let's kind of take a second and let's start looking at these four main types of reactions that we've. So this first one that we want to look at is what's known as a synthesis reaction. Literally, to synthesize just means to combine. So now in this case, I've got like A plus B makes compound AB. Essentially, the thing is this. What makes this what it is I've got multiple reactants. I've got a number of reactants over here. But take a look at the other side. What makes a synthesis is on the other side, I only have one single product on the other side, and that was terrible. One product. I've got one product on the other side of this. So like in the case down here, here's an example of a synthesis reaction. I've got hydrogen gas and oxygen gas, and usually if we were in a class right now, I would actually fill a balloon full of a hydrogen gas. And then I'd stick it with a match, and as soon as I did, boof, it would explode. And it's kind of a little cool trick. What happens is the hydrogen reacts with the oxygen, and what's cool is the only product it forms, it's water vapor, which is, if you're ever wondering why people want cars to run off of hydrogen, it's simple. If your car run off of hydrogen, your only byproduct would be water. So no greenhouse emissions. So it's a fabulous idea if we could ever actually get this going. So synthesis and decomposition are pretty simple. They're the exact opposites of each other. Where you have multiple reactants, and I just have like A plus B. The thing is, there could be 4 or 5 reactants and one product. The key is one product. So in the decomposition, what makes it what it is there is only one reactant. And the same thing, there could be any number of products. There could be any number of products on the other side. But the catch is there's only one reactant. And essentially what you're doing is you're breaking the compound apart. You're decomposing it. So here you've got the water, and this is where you would get the hydrogen. If you're wondering why we're not all burning hydrogen right now, it's because while we have a great source of water, it's the energy. It's not just, you can't just go and break or decompose the water. It takes a lot of energy to break down the water and make the hydrogen gas that you would need for the other process up here. And so that energy is what makes this like non-prohibitive in order to kind of be able to do this. So anyway, you take this and you break it apart into the hydrogen, the oxygen. And if you're wondering why, hydrogen's not going to exist as monatomic hydrogen. It's going to form a covalent bond with another hydrogen atom, and you get this hydrogen gas. If somebody wanted to really be nitpicky right now, the thing that they might be able to get on to me for is some people would write like the equation like this. And it's okay if you're that guy that's going to make somebody do this. Excuse me. These are called phase labels. So if you see these in the textbook or something, or your teacher's making you, all you need to know is that as we go through and we try and identify and we try and balance, these phase labels aren't going to change anything. You'll see things like this. S, L, G, and AQ are the phase labels your teacher might throw at you. S just means a solid. L means it's a liquid. G, it's a gas. AQ is actually, think about this, aqueous. It means it's dissolved in water. For a lot of reactions to take place, you actually have to dissolve the substance in water before it's able to react. And so we call that an aqueous solution. So I did not put that in any of these because it kind of junks up their reactions and what I'm trying to teach you. So two more, and then we'll kind of move on with this thing. So two more types of reactions. So like here's a single replacement reaction up here. So a single replacement reaction, what happens is this. You've got an element and a compound for the reactions. So you've got an element and a compound, and you will make an element and a compound. So you can always identify these because you will have on each side, look at this, there's an element, elemental aluminum, and then you've got a compound of cupric chloride. So you've got one element, one compound. Now look at the other side. You've got one compound and one element on the other side. So that's what we've actually got into this. So the big thing here, what happens is this. And the part where y'all kind of get messed up, and for some reason I'm unable to erase. Here we go. I'm going to try and erase this. What happens here is this. Y'all have problems, and we'll work on this later, predicting, well, Mr. Cole, how come it's not ALCU on the other side? And we'll work on more of these here in a second, or in the next video. Well, you got to remember, aluminum is a +3 oxidation number. Copper can either be a +2 or a +1 oxidation number. Well, aluminum's trying to give away electrons. Copper is trying to give away electrons, so it should make sense to you that they can't combine with each other. So when we look at this reaction, this is where these oxidation numbers pay off. This is a +2. This is a -1. So what happens on the other side, you got +3 and -1, which is why you had to have 3 chlorines on the other side. So we've always got to take care of these oxidation numbers, but you should be able to identify this single replacement reaction. Again, element, compound, element, compound. Hey, Mr. Cole, what happens if we wrote Cu plus AlCl3? Are we wrong now? No, it does not matter the order that you write down your products or your reactants in. So moving to the last, and we're going to finish this video. The last is a double replacement reaction. Now, double replacement is very easy. Compound, 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 compound. Say it with me. Compound, 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 compound. So here we've got hydrochloric acid and sodium hydroxide we used in an earlier example. So you've got two compounds, and you make two compounds on the other side. So this is a double replacement. One of the first things you're going to be asked to do is try and identify single replacement, double, synthesis, and decomposition. So anyway, you should be able to do that, and we'll talk about more as we go through and do some examples when we balance these equations. But anyway, we'll talk to you later. Bye.